Well, here's one for you. I'm not an outlier. I just haven't found my distribution yet. Get it? So, outlier for one is in a sampling or in a distribution for another. And today we're going to be talking about population distributions, sample distributions, but the main thing is sampling distributions. All right? But they sound the same. So, let's go ahead and get started. I surveyed all 96 students in my regular statistics classes to determine the number of children in each family. The average number of children per family is 3.28. So the graph and the table show the population distribution. Why is it a population? Well, I surveyed everybody. So if I'm only concerned about my stats students, this tells me that information. And luckily I have the power to do that. So what does this point represent? So you can see their responses right here, the number of children in the family and how many students responded. And that point right there is a response from one student. It represents one student in my population that has 4 children in their family. Okay. And we have a nice box plot as well. I thought I'd throw that in. So what is the population? The population is the 96 students in my regular stats classes. The parameter that I was trying to find is the number of children in a statistics student family, really the average number of children. If I did not have access to the entire population, I could estimate it by taking a sample. So let's pretend I couldn't see the whole population. And I'll just pick 10 random students, and I actually did. And this gives a sample distribution. So the population distribution is when I show all the values, like in a dot plot or something, for the entire population. For a sample distribution, I show all the values for each individual in that sample. So what does that highlighted point represent? It represents one student in my sample who has a family with 3 children. The sample is the sample of 10 students that I selected randomly. The statistic is the average number of children in the families in the sample. So population versus sample. We can make inferences about populations using samples. Now, statistics, if I were to take another sample, do you expect me to get exactly the same number? No, statistics vary from sample to sample. Parameters do not vary for a population at a given time. Now, if I wait a year, yeah, the parameter is going to vary. So there are probably more kids or different students and all that sort of stuff. But for an actual population at the moment you're trying to search it, there is a parameter. You may not know what it is, but I promise you it exists. It's not like Schrodinger's cat that may or may not be there. So before we were looking at the statistics of a single sample last semester. Now we're trying to infer information about a population from a sample. So before I might look at the number of band students in a single class, or the percentage of students who earn credit on the AP Stats test in 5th period. Now I can say, maybe I want to know the average number of students, band students per class, and the percentage of students in general who earn credit on the AP Statistics test. So we have different symbols for parameters in statistics, and you've seen these before, but let's review them. For the mean, that is mu for the population. So please use the right symbols. If you use the wrong symbols, you can get dinged. For a sample, it's X bar. It also can be Y bar or whatever variable you have bar. Variance is sigma squared. All right, that's for the population. For a sample, you can see it as S squared or S of X squared. When describing parameters, make sure to use words like all or true. That way we know you're talking about the actual parameter. If you are vague, we don't know if you're talking about the sample or the population. However, if you use the symbols, we know exactly which one you're talking about. So make sure you use the right symbol for the right number. So let's go ahead and do an example practicing identifying population, parameter, the sample, and the statistic. A high school student was interested in finding the mean annual tuition at a 4-year U.S. college. The student randomly selected 23 U.S. colleges and found a mean annual tuition of $19,800. So the population, who are they interested about finding information about? It's U.S. colleges, and 4-year, not 2-year, but 4-year U.S. colleges. All that information is given to me, and that's what we're trying to infer about. What are we trying to find out about the 4-year colleges in the U.S.? The mean annual tuition for those colleges. Now, what is my sample? My sample is the 23 colleges that I selected to measure. And the statistic for that sample is the mean annual tuition of $19,800. That is the statistic. Does that mean that I know the actual mean annual tuition for 4-year colleges in the U.S.? No, I don't. This is my estimate of the parameter. Now, we know because of randomness and variability that for different samples, I'm going to get different results. So when we do different samples of the same size from the same population and produce different values for a statistic, this is known as sampling variability. So we expect differences. So I thought, okay, well, let's pretend I didn't have access to the whole population, and I have my students take 100 random samples of 10 students. All right. The dot plot of the averages for these 100 samples is shown below. So what does that point represent? It represents the average family size of 4.8 in one sample, really of 10 families. All right. It does not represent one family with 4.8 children. It's just the average of the 10 families. So sampling distributions, the one I just showed you, is an approximate sampling distribution because it's too difficult for me to represent all the possible samples. And it's created, if I want to make an actual sampling distribution, and we can for certain statistics, then we have to actually record the sample statistics for all possible samples of the same size for the same population. So there are a couple instances where we actually can create these distributions, and we have to know a lot before we can do that. So let's go ahead and start with this example. Here, Mrs. Chauvette has an interesting approach to assigning grades in her stats class. Of the 5 tests students take throughout the semester, she selects a random sample of 3 and finds the average score of these tests and records this average as the student's final grade. So here are Joe's test scores. This is the population here, 93, 87, 96, 78, and 90. And we're purposely picking a very tiny population so I can show you a real sampling distribution. So how many different samples of size 3 can we create? Well, I have 5 to choose from, and I'm going to pick 3. Hopefully you'll remember combinations. It tells us that. Why is it combinations instead of permutations? Permutations tell you how many different ways you can arrange something. When I'm averaging, it doesn't matter if I pick 93, then 87 and 96, or 96, 87, and 93. It's the same sample. So I need to make sure that I take into account order doesn't matter in this case. And that's true for all these problems. All right. So I'm going to list all 10 samples of size 3. So I'm going to go 93, 87, 96. Then I'll go 93, 87, not 96, but go 78. And then do the 90. Okay, well, I've got all the ones with 93. Now I'll start with 87, 96, and 78. See them in the center there. All right. And then I'll leave out the 78 and put in the 90. And let's see. So I've got all the ones that have 93 and, oh, I'm sorry. I'll go with 93, 96, and 78. So I'm skipping the 87. Bad name. And then I skip the 87 and I get the 90. All right. Did I get all the samples in 93? I could probably skip these 2 and get those 2. All right. Now I'm going to start at the 87. 87, 96, 78, and then skip the 78 and get the 90. Now start at 90. Let's see. Skip the 78, 87, 96, and 90. So between them, I've got them all there. I'm forgetting my order. And then finally 96, 78, and 90. So those are all of the possible samples. So I can actually have a real sampling distribution. We're going to look at 2 statistics, the mean and the range. So you can actually take a statistic on almost anything you want. It doesn't always have to be the average. So let's go ahead and put the means in. We're usually doing means. And let's put the ranges in. All right, and you remember how to find range. Largest sample minus the smallest sample. All right. So I'm going to create a dot plot with those values. So first of all, let's do the mean. And there's the range. All right. You can see the mean when I did this ranged, well, went from 85 to 93. Okay. And for the ranges, I only got, interesting, much more clumped here. 6 to 18 is the range. Now, we know that the true mean of the population of Joe's test scores, we can just add them up, divide by 5, is 88.8. Well, guess what? When I calculate the mean of all these, I got 88.8 right there. So is the mean of the sampling distribution an unbiased estimator? In other words, is it close to accurate? Yes, because the mean of the sampling distribution is actually equal to the true average test score that it is trying to estimate. Now let's go ahead and take a look at the range. We know the true range of scores because we know the whole population is 18. Does the sampling distribution for the range seem to be an unbiased estimator? So I averaged all these results right here, and I get 12.9. All right, probably a little more that way. But anyways, you get the rough idea. Well, 12.9, the actual range is over here. Why is this happening? Well, because to get range, you need to actually have the minimum data point and the maximum data point in your sample, and that's just not going to happen. So in this case, the mean range of the sampling distribution is lower than the true range, and that is trying to estimate. It is a biased estimator, all right? It's not unbiased. So that's what we mean when we talk about unbiased estimators and biased estimators. When the samples we're taking will be close to the true value for the parameter. When it's biased, it won't be close to the true value. And there's other ways to get biased. For example, you can introduce response bias, and so you're going to have a biased estimator. So if I asked a question like, who's your favorite teacher this year? And I get a high proportion of overmen when you really don't mean it, that would be a biased estimator. You might feel pressured because I'm grading something of yours. So you get the idea. All right. In 2018, these are actual numbers, 203,855 students took the AP statistics exam. And I was very happy to see that 17 out of 41 of my students who took it scored a 4 or higher. Now, globally, 35.2% scored a 4 or higher. Is there convincing evidence that having 17 students score 4 or higher out of 41 is very unusual? So we'll get to the question in a little bit. First, let's draw the population distribution for the proportion of students who scored a 4 or higher. Now, if I did a population distribution for scores, that would look more like a dot plot. But for a proportion, it's really just the proportion who scored 4 or higher and those who didn't. So there you go. That's my parameter. And these are the people that scored 4 or higher. All right. So it's just a simple bar graph, relative frequency graph. All right. Then for my sample, it's the same thing. It's just, okay, I've got my 17 kiddos here and my other kiddos here, and my statistic was 0.415. All right. So when you're drawing a population distribution, it doesn't necessarily look like a sampling distribution. Neither does a sample distribution. Okay. So in fact, sample distributions are more like population distributions than sampling distributions. So if you want to have your mind blown, sampling distributions are distributions of sample distribution. Isn't that nuts? Okay. All right. So now I actually, because this is technically like a binomial, and I can actually model that pretty well. I actually used, I think I used GeoGebra to make this. And I put in the sample size of 41 and the proportion for the global of 0.352. Because remember, I'm trying to put the population value in. And this is an expected number of students to score 4 or higher out of 41. Now, in general, we actually are interested in proportions more than how many students, because I don't have 41 students taking the test every year. So I'm more curious about what my percentage is. So comparing year to year, I'm going to divide this out and then go ahead and calculate my percentages. And you can see there's my little guy right there. So I changed these numbers pretty much to their percentages. And you can see that for the population, it's roughly 0.15 to, oh, I don't know, about 0.5 some. Most people have anywhere from 15% to roughly 50, I don't know, 55 or 60% getting that, getting 4s and 5s. All right. The average is here probably, well, we know 35%, right? So the average is in here somewhere. Now, the reason it doesn't match perfectly is because I only have 41 people in this sample, and so I can only have certain numbers for the proportions. All right, so can we claim that having 17 out of 41 students score a 4 or higher is very unusual? Well, that's that part of the distribution. And while, yes, my children performed above average, and I'm proud of them, it's not unusual. In fact, I think, whoops, let me go back. If I got something like this over here, you know, or let's say I had a percentage of, yeah, let's say I had an 80% scoring 4 or higher. College Board might be a little suspicious and say, that's very unusual. Let's double check those tests and see what's going on. In fact, if you've ever seen Stand and Deliver, it wasn't because of an unusual average. It was another unusual thing they saw. They flagged the class and they had them actually retake the AP test for calculus because what they saw was very unusual. So there's always a lookout for things that are unusual, and that's what flags things. All right. So how does sampling size affect measures of mean and variability? So this is a cool applet. You can actually go here yourself. And I'm putting in, I'm just using this rough population distribution, all right? And we're going to take samples from it. These are samples of size 2. All right, so you can see there's 2 and there's the average. I'm going to keep taking samples of size 2 on the left. Then we're going to do samples of size 10. So I actually have to get 10 dots here before an average drops out. All right, see, this one's going quick and that one's going a while. Well, this is sample size of 25. So I actually have to have 25 dots come out here before it fills in a dot. All right. So there we go. Just got to wait for it to finish. And then I add a bunch of samples because it takes too long on that one. So what about the means of these various samples? Here is the true mean of the population. And here's the mean for my sampling distribution. Well, my approximate sampling distribution, because this is a simulation. Here's the true mean of my population, and there's the mean of my approximate sampling distribution. Ditto here. All right. The means of my approximate sampling distributions for all 3 sample sizes are the same. Okay, well, let's go ahead and compare the variability for the different sample sizes. Well, this is way more spread out, and then it gets less spread out, and it gets less spread out. So as sample size increases, the spread decreases. So here I'm saying the spread is going down as my sample size goes up. Why is that? Well, here, if I draw from the 2 ends, well, actually, I could draw 2 over here and get a very low average. And I could draw 2 over here and get a very low average. If I got them from both ends, the average is probably right there. But here, once I start drawing 10 of them, the odds of me getting 10 all the way over here is pretty low. Same thing over here. So I'm not going to be as spread apart. The odds of me getting 2 over in this area, not that low. So that's why I have the higher spread. Now you do 25, and you can see that it's even tightening up more. So which is better, higher variability or lower variability? Well, if we're trying to approximate something, and we know that it's the sampling distribution will give us a good estimate of the mean, so all of these give us a very good estimate of the mean. Am I more likely to be further away in this sample or this one or this one? Well, here, almost all my samples are really tight and close to the mean. Here, I can actually be, I can take a sample, but my estimate could be further away. So, lower variability is better because the individual sample statistic for one sample is likely to be closer to the parameter. So variability does not depend on the size of the population. as long as the sample size n does not exceed 10%. And I'll tell you why later on that one when we go over means. So why does variability not depend on population size? Well, imagine you had a pitcher of tea, all right? And we mix well to randomize, and we take a spoonful of tea to taste it, all right? Is that pretty, do you know how the tea tastes? Yes, you do. You got a sample. Now, let's say we make a much larger pitcher of tea. Will a spoonful still work for this large pitcher if the tea is mixed well? Actually, it'll be fine. Having a small pitcher and having a large pitcher, if we mix well, then the size of the population does not matter. All right, so that sounds weird having the yes there. Finally, let's go ahead and talk about bias and variability. Bias, bad. Variability, normal. I know a lot of you are like, oh, there's bias. If there's randomness, that doesn't mean there's bias. It just means there's variability. And that's variability is the nature of statistics. Do we try to minimize it? Sure. But variability is not the end of the world. Bias is. Now, where does bias come from? Well, as you saw, there are biased estimators like the range when what the samples pull doesn't really reflect it. Or if you have bad design on a sample where you put in questions that induce response bias, or you have undercoverage, or you have people not responding called non-response bias, or you take volunteers that overrepresent. So somehow it's not mixed well. That is bias. Bias, bad. All right, so first target we have here. Is this low or high bias? Hopefully you said it was high. Variability. No, there's very little variability here. All right, and we could achieve this by having any of those biases I told you about, but having it where it's in the design, even though we do the statistics properly. All right, this one has a low bias because on average, it's kind of close to the mean, but the variability is high. So this is not optimal, but it's definitely better. All right. And then this is the worst case scenario. You have high bias and high variability. We do not want that. What do we really want? We want low bias and low variability. But in a pinch, if you're stuck with this one, that's not so bad either. All right. So precision is more about variability, how tight your distribution is, and accuracy is more about bias. So increasing sample size makes an estimate more precise, not more accurate. And that's a common mistake on the AP test. Some students will say, oh, I'm increasing accuracy by taking a larger sample size. Ding, do not write that. That's not true. Increasing your sample size increases your precision, all right, not your accuracy. But if you eliminate bias and you have a great sample size, hopefully you will be accurate. But it's very hard to claim accuracy, so be very careful about that term.